Okay, everyone. So our next speaker is Ken Golden from the University of Utah. He'll be giving a two-part talk on multiscale analysis of sea ice, which I think we'll see has some nice connections to the partial melt problem. And just a reminder, there's a coffee break between the first talk and the second talk. All right, and now we have Ken Golden.
Okay. Well, thanks, Gideon and Dan, for inviting me. I was a little surprised as a guy that goes to frozen parts of the world to be invited to talk about melting in the mantle, till I looked into it a little bit and I saw, oh, I get it, I see. And in fact, basically, all my talk is Wen-Lu's talk minus 1,000 kelvins plus some math. It's the same talk. So anyway, so I'm a CI, kind of a composite materials, sea ice, statistical physics type of person. And this is actually sea ice in the Arctic Ocean that's melting. This is just one of the sort of interesting melt problems associated with sea ice. But I think you'll see a lot of the techniques and a lot of the ideas that have already been coming up this morning, I think you'll see arise in our sea ice problem. And pretty much I'd like to show you kind of some of the mathematics, in particular multiscale mathematics and ideas of homogenization, percolation theory, and so on, that we've developed to try to understand sea ice and in particular its role in the climate system. Now, I thought, I really should start by at least kind of justifying a little bit for why you should listen to somebody who does mathematics of sea ice. And I immediately found one of Wen-Lu's beautiful pictures. So this is partially molten rocks here versus sea ice, and this is some of her X-ray tomography that you've just seen a whole lecture on, how there's 2% melt. This is the melt X-ray tomography of the melt phase, 5%, 10%, 20%, and so on. And here is some of our X-ray tomography of the brine phase in sea ice. So sea ice is a composite material of pure ice with primarily brine inclusions, which are basically the melt phase. There's also a little bit of air as well. And again, this is some of our X-ray tomography. There's some different structure, but there's an awful lot of similarities, as you will see. Okay, now I need to tell you a little about sea ice and kind of some of the story behind sea ice and motivate some of the problems that we look at. So I do need to tell you a little about the Antarctic and the Arctic, and in particular the cryosphere. So we're talking about the frozen portions of Earth's surface. Now, one of the principal things that gets studied in the polar regions are the great land ice sheets, which are, say, 2-3 miles thick of pure ice, and that has a very different microstructure. That's like the ice in your ice cubes, different microstructure than what we're interested in. What we're interested in is the frozen seawater, say, in the Antarctic surrounding when the Southern Ocean freezes. And even though I'm a professor of mathematics, I'm a bit of an unusual professor in the sense that I've been to the polar regions now 17 times. And so I've been 7 times to Antarctica, twice in the Weddell Sea. My first trip was in 1980 when I was an undergraduate to the Western Weddell Sea. And I think we were the second scientific expedition into where Shackleton, the famous expedition of Shackleton, had gone. I've also been on the Ross Sea over here. And a lot of my expeditions have been with the Australians off the coast of East Antarctica down there. In fact, actually, I'll show you at the very end a little pre-wine reception entertainment. I'll show you a video of our most recent Antarctic expedition with the Australians in this region. Now, in the Arctic, aside from just being geographically opposite, where in the Antarctic you have a continent surrounded by ocean, here you have an ocean surrounded by continent, the great land ice sheet in the north, of course, is the Greenland ice sheet. And what we're interested in, of course, is the frozen Arctic Ocean. And so I've been up to Barrow about 9 times, I guess, and up on a Coast Guard icebreaker a couple years ago up into the Chukchi Sea. And in fact, I'll actually be up in Barrow in a few weeks again. And okay, so what is sea ice? Why study it? Well, even though it is melting, there's still a lot of it. In general, it covers roughly 7 to 10% of the Earth's ocean surface. It forms the boundary between the two principal geophysical fluids on the Earth, namely the ocean and the atmosphere. And as such, it mediates the exchange of heat, gases, momentum between the ocean and the atmosphere. Here you see, this is actually the lifeboat of the Aurora Australis, which we almost wound up in my first time with the Australians. The ship kind of caught fire. It was kind of an exciting adventure. And here's heat rising up through a lead through the ship's track of the Aurora. You see this heat exchange process. But both the melting and the freezing of sea ice play a large role in global ocean circulation. It's one of the main ways that the polar regions communicate with the rest of the world's ocean system and climate system. And as this very thin frozen layer, not 2-3 miles thick like the great land ice sheets, but 1 meter, 2 meters, 3 meters in that neighborhood, although it can get crunched up, as you'll see in the video, it can get really, really thick by crunching together. Sea ice is not only a very sensitive leading indicator of climatic change, but it's a key player in Earth's climate system. And one of the main roles that it plays is in reflecting incoming solar radiation during the polar summer. This is measured by the albedo, the ratio of reflected sunlight to incident sunlight, and whereas white snow and ice reflect most of the incoming solar radiation, ocean water or for example, meltwater sitting on the surface of Arctic sea ice absorbs most of that incoming solar radiation. So one of the main roles is kind of protecting the ocean from absorbing too much solar radiation. So a lot of that's getting reflected with a classic white polar ice cap, but as you start to lose that white polar ice cap, then a lot of that radiation is absorbed rather than reflected back into space. And of course, that's the issue, is that particularly in the Arctic, we are losing that summer Arctic ice pack at a rather dramatic rate. This is the long time average over the satellite era up till 2000 of about 7 million square kilometers at the minimum during September, at the end of the melt season. And you see sort of a gradual decline. And then things really got, around the turn of the century, things really got going. This made the news a lot in 2007 when we hit a record low. We bounced back a bit, and then we had a new record low in 2012. I think that was on September 13th. I remember that because on the Antarctic expedition, I'll show you the video on at the end, that was the low, I think about the day we left, and it was about 3.41 million square kilometers. And so now you can make the rather dramatic statement that we've lost over half of the summer Arctic sea ice pack, not in millennia, not in centuries, but over a decade or two, which is pretty amazing. Okay, to put this in some geographical perspective, here the area in red is what's been lost basically over this period of time. And so one of the things that's happening, as I mentioned at the beginning, is instead of that white icy surface to protect the Arctic Ocean, well now that's gone in the height of the summertime, and so that solar radiation is being absorbed, which further warms the ocean, which melts more ice, which exposes more dark surface, and so on. So it's a positive feedback loop called ice albedo feedback. Now, from a modeling perspective, these are the famous IPCC runs, but this is from 2007. And so whereas all the world's best climate models predict general declines of summer Arctic sea ice over the 21st century, here's, say, the mean, what's striking about this is that's the real data. In other words, the ice was melting much, much faster than any of these models was predicting. So that raises the question and a challenge, well, what's going on? What are we missing in the models? Are there other types of processes that are happening? Can we represent sea ice more rigorously in climate models and account for key processes which had not been included previously, such as the evolution of these ponds on the surface? And there's another fundamental problem that comes up throughout the sciences and engineering, and in particular in my business of composite materials, and that is this issue of linkage of scales. In other words, these big global climate models, you're talking about 50 kilometers of scale between the grid points. I will be talking about sub-millimeter, I'll be talking like a frog, sub-millimeter scale processes like fluid flow through the porous microstructure and how that affects these larger scale processes. So there's a fundamental issue of linkage of scales. And in fact, that's really sort of the area of mathematics and physics that I come out of, homogenization, statistical mechanics, these kinds of areas. And basically what I've done in my career, certainly the last 10, 15 years, is to bring to bear these techniques of composites and statistical physics and apply them to sea ice and maybe potentially to some of these other interesting areas, problems that you guys are interested in. Okay, so sea ice may appear to be just a barren, impermeable cap. Actually, that's Hayo Aiken, one of my closest colleagues, who actually did a lot of the X-ray tomography work that a big project we had together with NSF. This is actually one of my the first student I brought to the Arctic, she was a freshman in one of my calculus classes. I teach these big calculus classes, and I kind of tell them all about penguins and all sorts of stuff and defy their perceptions about what math is. But, and so this was many, many years ago, but you might think it's just in a barren, impermeable cap. However, it is a porous composite material of pure ice with fluid, the melt phase, the brine inclusions. And this is sort of the millimeter scale. This is way down looking some scanning electron microscopy from Rachel Obard at Dartmouth and Krell. And also these inclusions can connect up and form these channels. This is a vertical cross section, a picture I took in the Arctic, and then a slice, a horizontal slice through that showing some of the interesting structure there.
How high does the concentration get in the brine channel?
Oh, in the, okay, so actually, so we've measured, taken brine out of what's called a sack hole, and we've seen up to, so seawater is 35 parts per thousand. We've seen up to about 180, 200 parts per thousand salinity in the, I guess you would have to say, the brine phase itself.
Is the ice, is it amorphous or is it forming a polycrystalline?
It's a polycrystal, and you'll see. Good timing. And so this is sort of a cross-section of these sea ice structures. And so as the ice grows, it forms this dendritic platelet structure, and it's sort of like it's trying to reject the brine. In fact, we have some of the world-renowned experts, Andrew Wells and some of his colleagues. There are a lot of people here in Cambridge and Oxford that really do this kind of stuff and do it very seriously and do it very beautifully, and to study these kinds of processes and so-called mushy layer theory and so on, treating sea ice in that way from a more metal theory perspective. So it's trying to reject the brine, but you get the very salty water gets trapped in some sense in between these platelets of ice, with these little individual crystals with the c-axis pointing perpendicular to the basal plane. And so when you get an initial skim of ice, a tiny crystal sort of floating, and in fact it looks like grease. I think there might be some images in the video I show you. Looks like grease on the surface, called grease ice for that obvious reasons. And then, you get a random distribution of the crystalline structure, but then as you form an initial skim and you're now growing in quieter water, then you get these larger crystals, and then they start to, so that the c-axes become horizontal. And this is just looking under cross polarizers, a thin section of sea ice. And of course, the freezing point is, not whatever, 1350 or whatever, it's minus 1.8 degrees Celsius here. Yes?
That's why you get the preferred orientation of the c-axis in the horizontal plane?
Okay, that was my first paper in Journal of Geophysical Research. I'll tell you about that in a second. About in the late 1970s, 1970s, they were using ground penetrating radar to try to measure the thickness of the ice. Still a very important problem. It's the holy grail of one of the holy grails of climate science now. It's hard to get your hands on that. I'll explain some of that later. But what they were seeing was that if you polarize the wave like this, you get a nice big bounce, a big reflection back from the bottom of the ice. You turn it 90 degrees, you get nothing. What's going on? And so that was how I got involved in composite materials. It turns out that if there's a well-defined long-term current direction, the c-axis tends to point parallel to that so that the brine microstructure is perpendicular, so you get a strong degree. There's a natural vertical anisotropy in the brine microstructure, but this induces a high degree of horizontal anisotropy as well. And so we modeled that using composite materials theory and looking at the effective complex permittivity of arrays of ellipsoids aligned in a certain direction, and we were able to pretty much reproduce all the results that they were seeing with this horizontal anisotropy.
Yeah, but why you get it?
That's a really good question, and I've never really seen I've never really seen a good theory laid out for that. There was some probably heuristic chemical analysis done by Tony Gao a long time ago, and Willie Weeks, who looked at that. But I wouldn't say it's really well understood. That's a good question, though.
So am I right in reading that the whole thing is about, you think about 2 meters depth?
Yeah, that's right. That's right. Yeah.
What is the eutectic temperature?
I think about minus 22 C, around in there, where it all finally freezes out. Yeah. Okay. Now, from my perspective, sea ice is a fascinating composite structure exhibiting its interesting properties on over about 10 orders of magnitude. It's a composite structures on many, many length scales, the sub-millimeter scale brine inclusions, the polycrystalline structure, which I'll talk a fair bit about later. These channels that form, these are cross sections with all kinds of fractally structure. These are massive brine channels in the Arctic, are really cool. You have to take this massive, like it's a chainsaw with a bar the length of this on train tracks, and then you slice down. These are really cool experiments, and then you pull the ice up with this massive gantry, and then you could get it behind the sun, and you get these incredible images. This is pancake ice forming in the Southern Ocean, which forms in the presence of waves. Again, I view this as a two-phase composite. In fact, I have a PhD student working on homogenized wave properties as it propagates through situations like this. Moving up in scale, larger blocks of ice, again, composite structure. That's the Aurora australis right there, about a length of a soccer field or football field, about 100 meters or so. And this is sea ice off the coast of Japan. Again, a time-evolving two-phase composite from my perspective. Okay, so basically what's this whole talk about, including the second part after the coffee break. So basically what I'm doing is I'm giving you an overview of the mathematical models of composite materials and statistical physics that we've developed to study sea ice and improve climate models. In particular, I'll also show you a lot of our field experiments as well that we've been combining with this. And however, and particularly here, I've tried to focus on problems and methods that might, from a completely novice's naive point of view, because I don't know you guys, I don't know what your problem, I'm starting to find out, and I see they're very close, but I want to at least try to focus on problems that might have some relevance to the things that you guys study. I want to talk just a little about what I call the opposite poles, no pun intended, the opposite poles of climate modeling. Big numerical global climate models versus simple toy models. I think, conceivably some toy model ideas might be useful for some of you. Specifically, the next section that I will be talking about in this talk, sea ice microphysics and composite structure, fluid flow, percolation theory, homogenization, and so on. A lot of the things overlap with Wen Liu's talk. I will also be talking about electromagnetic monitoring, more kind of remote sensing motivated, but again, it's basically very sophisticated techniques of homogenization, and some of the things that we found in this context. And then finally, I will talk a little about these melt ponds as well and their fractal geometry and some of the methods that we've developed to look at them. And then actually, and finally, at the very end, and as I said, the pre-wine reception entertainment, I'll show you a 10-minute video, which actually gets into the experiments and so on, but it's also just kind of fun and interesting with penguins and what you'd expect from Antarctica. A couple of the key points that run through my talks. The notion of critical behavior. Wen Liu talked about a percolation threshold. That's what I'm talking about. In other words, critical phenomena where small changes in the parameters of a system induce very large changes in the effective or overall behavior. But also, something that I believe illustrates the power of a mathematical approach is what I like to call cross-pollination, where you take ideas and techniques from seemingly completely unrelated areas of science and engineering or medicine and apply them to sea ice, and vice versa. You'll see some interesting examples of that. Okay, so just a word about these big global climate models. This in your context would be some huge multi-scale simulation where you've got things going on the micro scale and you're trying to simulate all kinds of flow and certain regions of below the earth, in the Earth's mantle and so on. A really large-scale model, where you're trying to include as many of the bells and whistles of the physics that you can. Okay, that's these big climate models. And of course, climate results from complex interactions between all the different components, the atmosphere, the cryosphere, lands, and so on. And, but these climate models are big systems of partial differential equations derived from the basic laws of physics and chemistry and fluid motion. And of course, they describe the state of the system as well as how all these different pieces interact. And here's the fundamental problem, though, is that these equations are solved on three-dimensional grids, such as these, but with the most powerful computers in the world. These are such complicated big models that the best you can do for a global climate model that you want to run for, say, 50 years or 100 years or whatever, is to have a very coarse grid. And of course, then one of the fundamental problems is how do you rigorously incorporate these important subgrid scale processes into these types of models. And that's kind of some of the flavor and motivation for kind of what we're doing. Now, just to give you a sense as to the sea ice components of this, what goes into these, what are the key ingredients? Well, probably the single most important one that's been around for about 30, 40 years now is this ice thickness distribution evolution equation. In other words, the probability of finding some ice of thickness h at the point xy at time t. And it's this nonlinear kind of advection diffusion type of equation with lateral melting, vertical melting, and then this crunching term which incorporates all the mechanical effects, how you can change the thickness of the ice, not through melting or freezing, but through crunching, basically, and forming ridges like this. There's been a very interesting development in that I'll just show briefly on the next slide that I know at least a few of you are familiar with because you know this person. Basically, F equals ma for sea ice. In other words, all the different influences, the drag from the ocean, the drag from the atmosphere, the Coriolis force, sea surface tilt, and the internal forcings as the ice pack interacts with itself. And I will spend a fair bit of time on so-called advection diffusion equations. This is in the context of sea ice, but I'll do it more generally as well. I would imagine that some of you are interested in convective processes in the mantle, I assume. And anyway, so I will talk a fair bit about the heat equation associated with this, but that'll be towards the second lecture. Okay, this just a little more about the ice thickness, and actually one of the things I had in mind, it's like, okay, this is the thickness of the ice flows. If you could also envision, okay, you've got all this convection in the mantle, you've got the ice flows are like the crust of the earth, and kind of floating around. And just out of curiosity, did you have any kind of correlation, with this kind of stuff? Or the mathematics there, could you tweak these kinds of approach and potentially describe the relative thickness? I mean, I don't know. I'm not an earth scientist. I have no training in this and anything. But anyway, so this is this ice thickness distribution evolution equation with all the different pieces, the velocity field, the thickness h, and so on. And anyway, this is what is solved in these big climate models is partly this, or certainly in the sea ice components of this. And there was a very interesting development by somebody who's probably, I think, well known here in Cambridge, is John Wetlaufer, and I think one of his PhD students. And I know that John is very close to Gray Worcester, who I know is here in Dampt here. And anyway, so John made a very interesting breakthrough. In other words, viewing that the ice thickness distribution equation basically as the thickness as a diffusion process with a probability density, and then the probability density is going to basically satisfy a Fokker-Planck equation. It's the generator for a diffusion process, and then this is the Langevin equation that goes along with it. And he's got really great correspondence. I mean, it's a very beautiful point of view, and I think probably one of the biggest breakthroughs in this component of sea ice physics in quite a while. Okay, now at the completely opposite end of the spectrum, you can ask questions. Now I want to talk about these little toy models, what are called toy models, low-order models where instead of having hundreds of coupled partial differential equations describing everything, you try to reduce the entire Arctic climate down to one nonlinear ordinary differential equation, for example. And you get a lot of controversy on both sides. In the global climate model business, it's like, well, they're so complicated and you've got every bell and whistle, do you really know what you're looking at? Versus, how could something so simple be at all realistic? But I believe certainly that they both have things to say, and they're both kind of an important point of view. Tipping point, there's a lot of tipping point issues, and this has a very well-defined mathematical meaning in terms of dynamical systems and so-called bifurcation theory, saddle node bifurcations and so on in the associated dynamical systems. And there's a lot of questions, such as the loss of summer Arctic sea ice, the melting of the Greenland ice sheet, the melting of the West Antarctic ice sheet. Particularly interesting is the shutoff of the North Atlantic thermohaline conveyor belt, which would affect weather and climate in England, Northern Europe, and so on. And these can be formulated in terms of these tipping point questions. Now, where this all comes out of, I'm actually teaching a course right now in mathematics and climate, and it's kind of cool, I think, out of such simple arguments, you can get really very interesting behavior. So just simply balancing the energy in terms of energy in, basically is whatever's coming in from the sun, basically, and this is called the co-albedo. There's the albedo, there's the co-albedo. In other words, this is what's absorbed versus what's emitted by the Earth at a particular temperature, assuming it's a black body, and then the rate of change of temperature is just this balancing of energy. And to get the equilibrium temperature of the Earth, you just set the, look for equilibrium, and you get, you actually get a value that's not so, that's not crazy at least, -1 degree Fahrenheit. You balance these two pieces. There's the E out, that's that guy. There's the E in. The balance point, the equilibrium point, is where you set these things equal. You can just solve for these physical parameters and come up with an equilibrium temperature. The next step beyond this is to parameterize cloud effects and the so-called greenhouse effect, to put an epsilon in front of how much gets out, and then you can get a much better result, which is much closer to the actual temperature. However, the albedo is the key parameter. And the most trivial models, people are assuming that it's just a constant. However, the next best guess is that it depends on temperature, and that when it's cold, it's reflecting, and when it's warm, you're absorbing. And so this is the co-albedo. And then now you get, instead of just two straight lines, now you get these multiple equilibria, like this. This is an unstable equilibrium. This is a stable equilibrium. It's kind of like what the state we're in, and this corresponds to snowball Earth, which there's apparently evidence in the geological record, I'm sure you guys know something about this, that shows that apparently there were 3 or 4 of these kind of snowball Earth situations. And kind of the idea of this tipping point and these bifurcations is that this is the first branch, the stable one, unstable, stable. The idea of a tipping point is that, okay, you're warming, everything's fine, you're just warming the system. You think everything's going to be fine, but then, ooh, it jumps. It jumps to this completely different state. And then if you want to get all that ice back, you think, oh, I just got to lower the temperature down to the same where I lost it. No, it's a hysteretic process, and that's one of the key features of these tipping points and these bifurcations is, well, to get down there to that branch, from up here, you got to go all the way down, and then you can drop down. So this is one of the fundamental features. And there's a beautiful, so then putting that in the context of sea ice, this would be unstable, stable ice covered, stable ice free. So this would kind of be the bifurcation diagram that you might expect in the loss of summer Arctic sea ice. However, there's been some very beautiful work. The initial paper was by the same John Wetlaufer and a good friend of mine, Ian Eisenman, in PNAS in 2009, where they derived a beautiful nonlinear ODE for energy in the upper ocean. They look for bifurcations, multiple equilibria, but in the case of the loss of summer ice, they don't really see a bifurcation structure. However, in the further loss of winter, you get much, much warmer. In the loss of all the winter ice, then they see a bifurcation structure. However, a follow-up paper with Dorian Abbott at University of Chicago and Mary Silber and Ray Pierre Humbert, they looked in some of the effects that happen when you lose the ice, such as clouds and the other effects of ice loss, and they see a more robust bifurcation structure. With a postdoc of mine, Ivan Sudakov, we looked at a little bit of the existence of multiple equilibria as you start to include melt ponds as well, but I'm not going to talk too much.
When you say robust, is that good for us or bad for us?
Bad for us, in the sense that there might be a tipping point, in the loss of summer Arctic sea ice. That's the point. Okay. Oh, okay. I had to split. I apologize. I had to split these PDF files apart. There was a problem with my Adobe Acrobat. So let me go in there and get the second one. Okay, there we go. Okay. All right, so now let's focus on more what Wenlu was talking about, namely fluid flow through the porous microstructure of sea ice. So it turns out that a fluid flowing through the, first of all, it's interesting because most people think, oh, it's just sea ice, it's just ice. Well, no, it has a complicated life of its own with fluid flowing through it and so on. It's a much more dynamic material than one might expect if you don't know much about sea ice. And so fluid flowing through the porous microstructure of sea ice governs really important processes, both climatologically as well as biologically. So for example, the evolution of these melt ponds, which basically determine the albedo of the sea ice, which is one of these very key parameters in climate modeling, whether or not these ponds pool up and grow or simply drain overnight, completely changing the permeability, depends, changing the albedo, completely depends on the permeability of the sea ice beneath the melt ponds. Also, the food webs in the polar oceans, I believe, are the richest in the world. And the base of those food chains or webs is the algae that lives inside the brine inclusions and sea. So I assume you don't have algae living inside your fluid inclusions in the melt phase.
But roasted really nicely.
What? Sorry?
Nicely roasted.
But then again, you never know. Who knows? You know, who knows? You might find some kind of incredible form of life or something. But anyway, and the way they get their nutrients is through fluid flowing through the porous microstructure of the sea ice. There's a lot of other processes. I will talk about a couple of these a little bit further down the road in this part of the talk, which could potentially be something. I don't know. You might see. Who knows? You might see something like this in your system as well. Okay, so you've all seen Darcy's law. Darcy's law for slow viscous flow in a porous medium, where we relate the average fluid velocity to the pressure gradient. I think of this entire parameter as like an effective fluid conductivity. The denominator is the viscosity and the numerator is the fluid permeability tensor, and this is an example of really, again, the business that I come out of, namely homogenization, which is the mathematics for analyzing effective behavior of heterogeneous systems, such as the effective electrical conductivity, thermal conductivity, complex permittivity, and so on, transport properties of composite materials. Now, to put this a little bit in a mathematical context, you can actually derive this from the basic Stokes equations for fluid flow, where you have a scale parameter epsilon, and essentially, as epsilon goes to 0, you're taking the microscale to incredibly small, or you're letting the system, taking the infinite volume limit of the system. And you can do a 2-scale homogenization, where you have sort of 2 scales. There's this fundamental microscale, but then you could also have the macroscopic properties of the material varying in space, but over much greater length scales. And that's pretty much what we have in sea ice, where on the microscale, you kind of homogenize that out, but then you have some dependence, say, on the depth, for example. So then the macroscopic equations anyway, it's called a 2-scale expansion. It's a fairly well-known technique in homogenization theory, led by initial results led by these mathematicians here. And so anyway, you wind up with by homogenizing this whole system, you wind up with Darcy's law, basically, with an effective fluid permeability tensor, and that's one of the main things that we're interested in. Okay, so as I said, homogenization is a kind of a very pervasive issue and field that comes up throughout the sciences and engineering, just roughly speaking. So here we have an inhomogeneous material, say a 2-phase material, conductivity sigma 1 and sigma 2. So you might imagine these are the brine inclusions. They might be salty water conducting inclusions in an ice host, where the conductivity of the ice is relatively small comparatively. And then you want to step way back from this, and so this black and white becomes kind of gray, and so, you know, in other words, there's all that microstructure there. And the overall idea is to find the homogeneous medium, which behaves macroscopically the same as the inhomogeneous medium. And so, interestingly, there's a lot of very famous scientists who have looked at this, going back to Maxwell, who derived at least the first term in the that shows you how difficult. This is Maxwell we're talking about, and then ultimately Einstein. What they were able to do was to derive the first term, the dilute limit, the first term in the Taylor series expansion in volume fraction in phi, which the melt phase parameter, for effective conductivity of a dilute suspension of spheres, and Einstein worked on the effective viscosity of a dilute suspension of rigid spheres in a fluid. Later on, Wiener, this is the arithmetic and harmonic mean bounds and the effective conductivity. I believe that's what Wen-Lu called parallel and series, those bounds. And then the next big breakthrough was that Wen-Lu had in her talk as well, the so-called Hashine-Strickman bounds, which are variational bounds on the effective conductivity and other transport properties of 2- and multi-phase composite materials. And this breakthrough here was one of the big steps forward in our use of, as societies, of composite materials. I think we all know lots of applications on how composite materials are used in transportation, in cars and trains and planes, and, you know, we are composite materials, basically. And anyway, so this was a very important breakthrough and kind of helped lead to the explosion because you got beyond just trial and error. In other words, now you had real mathematical bounds on how good can it be, how bad can it be, and so on. Okay, now, just to give you just a little bit of a sense of this, of homogenization, kind of where this comes out. So let's look at and this is almost exactly the problem that Wen Liu was looking at, the effective electrical conductivity of a two-phase composite, local conductivity, sigma 1 and sigma 2. Local constitutive law, the current is sigma, the conductivity times the electric field. The current is divergence-free, the electric field is curl-free. This local constitutive law becomes this macroscopic constitutive law, which defines the effective conductivity, sigma star, for this material where sigma 1 is in the volume fraction P1 and sigma 2 is in the volume fraction P2, where P1 plus P2 is 1. And in general, this homogenized parameter, this effective conductivity, is a very complicated function of the ratio of the constituent parameters as well as the composite geometry. And there are Wiener did this in a certain way, but there are very simple, beautiful energy variational principles where you can almost, in just a couple of lines, derive these rigorous bounds on the effective conductivity of this two-phase material. That's it's an attainable bound. It's realizable in the sense that there's a real material that you can construct that attains that bound, and so that's in parallel, the arithmetic bound. And then the lower bound is, so this is anisotropic, of course. The lower bound is the so-called harmonic mean bound, which corresponds to this configuration, so in series, basically. Okay, so now, in fact, you almost had a slide like this relating the electrical properties to the fluid properties. So when I first started getting involved in the fluid permeability of sea ice and trying to address that from a theoretical point of view, I thought that, we should just be able to find in other words, the analogs of the arithmetic and harmonic mean bound should just be like that. It's like, okay, come on, how hard can it be? Well, it's a lot harder than I thought. And anyway, part of the issue is exactly the point that Wen Liu was raising. So for a cylinder, electrical conductance, the area times the conductivity of the material, but then the electrical conductivity divided by the area, it's just a material parameter. But now if you have a pipe of radius r, the corresponding fluid conductance scales like r to the fourth. So when you do it per unit area, you still have this extra length scale that's involved, and that's what makes the problem so hard. And the bounds are very different and so on, and much more involved from a mathematical perspective. So basically, the first question we asked was, if you want to get an upper bound on the vertical fluid permeability, the vertical component, that's what we're most interested in the sea ice case. I would think that's probably at least what you're most interested in this case as well. The question is, what's the attainable optimal material that gives the largest of the permeability? In other words, how do you arrange the inclusions under certain constraints that we have in sea ice so that you maximize the vertical fluid permeability? And basically, it's going to be these hierarchical sets of pipes that come out. They're basically the so-called Hashing-Strickman coated cylinder geometries. And so what we've produced is the fluid analog of the arithmetic mean upper bound on the effective conductivity, at least in the case of sea ice. And this is based on some very beautiful optimal void bounds found by a friend of mine, Sal Torquato at Princeton, and I think one of his PhD students, published in Phys Rev Letters in 2004. And what's interesting here is you have to take a completely roundabout way to actually prove these. Namely, you have to analyze what's called a trapping constant for a diffusion process in the pore space. And so to kind of set this up, just to give you a flavor of what's involved, so you have a diffusing tracer with concentration C of xt reacting with traps on the pore boundaries. And so this is the basic equation. There's the reactant source rate, the diffusion constant, so on. And then you have boundary conditions, where kappa there is the surface reaction rate. And then you can define with a scaled concentration field, which in steady state that satisfies absorbing boundary conditions, satisfies this Poisson equation, and then the average of that is this so-called trapping constant. And then there's, similar to the electrical problem, There's a variational inequality for a lower bound for the trapping constant, and this is one of the standard ideas in homogenization. You get these sort of an energy inequality, and then the idea is that any field any electric field, or in this case the fluid-related field or the concentration field that satisfies the fundamental mathematical conditions and the boundary conditions, any field that plugs in, that you can plug in there, it gives you a bound. Might not be a good bound, but it gives you a bound. And the idea is you want to search for better trial fields that give you these really good bounds. And this is also then this trapping constant is then related to a mean survival time. How long, in other words, when it hits the boundary, it gets sucked in. And so how long might a diffusing particle survive? And so this is the kind of trial field that's used basically based on the, because you want to satisfy that the Poisson equation. So you have basically the free space Green's function for the Laplacian. And essentially there's a lot of work that goes into this now, but then you get this rigorous lower bound on the trapping constant involving the solid phase, that's 1 minus the brine volume fraction, divided by this length scale, which involves the 2-point correlation function of the pore structure. And then you can evaluate those bounds for the for these Hashing-Strickman coated cylinders, which are optimal in the homogenization context. And then you get this, so the bound that on the trapping constant involves the ratio of these moments of the radii of the inclusions, which I assume you guys have some information about in your melt case. And then there's a rigorous bound on the which is what we want now, on the permeability in terms of the trapping constant. And then that leads to what I call our log normal pipe bounds, because then it turns out, as I think somebody here noted before, in your case, at least maybe that was for the grain sizes though, but in our case the fluid inclusions, they behave log normally, and so they're normally distributed with mean mu and variance sigma squared. And so again, we do more calculations. Turns out that my colleague worked on this. He actually worked on Wall Street. A lot of the same calculations come up there, so he was able to very quickly figure out what we needed to do there. And so there's the rigorous upper bound, and there's a lot of our data, field data as well as some laboratory data as well. Now what's interesting about this, usually these bounds, this is such a kind of gross assumption, that kind of, these pipe microstructures, you might think that, your bound is going to be orders of magnitude, it's going to be a bound, but orders of magnitude above the actual data. But you see it's pretty close. And that's because there is a natural pipe type structure to the kinds of brine structures that you see in sea ice. Okay, so now essentially on to the connection with Wenlou's percolation threshold. So certainly one of the things. Oh yeah, sorry.
I have a question, and I think someone else does.
Okay.
So the first question is does anyone have a result on a lower bound, even if it's crude?
Not that I know of. Yeah.
For your upper bound, what's the sort of length scale that's sort of giving that upper bound, and what does that correlate to in terms of, you showed this picture of sea ice which looked more like platelets, so sort of vertical.
Yeah, that's a different part of it. That's the ice part. We're focused now on the fluid phase, which does form these structures like this, like these river types of structures.
Length scale for those channels?
No. The important part is the length is the horizontal length. Basically, in the end, you get these big pipes, but it's really the size distributions of the widths of the inclusions in the pipe. That's what goes into it. In other words, the key ingredient is this Paravigian Gal. The cross-sectional areas have a log normal distribution. That's where the key length scales come in that give the bound. Okay, so. One of the most important phenomena that I've ever discovered in my life is effectively an on-off switch for fluid flow in sea ice. I first got an inkling of this by just looking at a really old, what used to be called the Sea Ice Bible that was published in the 1970s, I think, and it looked at, it was change in salinity. It was like the change in brine drainage kind of stopped below about 5%. And I kind of had that in the back of my mind. And anyway, then I was in Antarctica in 1994 about midnight in a big storm, and all of a sudden I saw seawater percolating up and flooding the surface. It was very dramatic. It wasn't like a fountain, but it was very dramatic for me. And I'd been studying sea ice microstructure since I was an undergraduate, and so I kind of immediately realized or thought, hey, this is a percolation threshold. There's a critical point. There's a threshold that has just happened where things have linked up and now the fluid can flow up. And the idea was, in this situation, you've got ice, now, and it's in the middle of a storm. You've got snow falling down, pushing the ice down. The water wants to come up, but it can't unless it has a pathway to the surface. And it was basically, I witnessed the final formation of these pathways, namely the threshold where you start to get fluid flow. And so, roughly speaking, for brine volume fractions in so-called columnar sea ice below about 5%, it's effectively impermeable. For brine volume fractions above 5%, it's permeable, fluid can flow, and increasingly so with increasing brine volume fraction. In fact, it's the same, I think it's the same variable that you guys were using. And so, by a coincidence, by anyway, something called the Frankenstein-Garner relation that relates temperature, brine volume fraction to temperature and salinity, this critical brine volume fraction, about 5%, corresponds to a critical temperature of -5 Celsius for a typical bulk salinity of 5 parts per thousand. Hence, this has become known as the rule of fives. You have a rule of threes, or something to that effect. Okay, why is this so important? Well, this surface flooding that I witnessed, about 25% of the ice that's created in the Antarctic ice pack is created in this way. Seawater, flooding, possibly from the side, but mainly from coming up, flooding the surface, and then the storm goes away, it gets cold, and then that stuff freezes. I'm curious if you have a similar kind of Antarctic surface flooding and snow ice formation in your context, where you have stuff going on and it finally gets too cool and it just kind of freezes, you know? Yeah.
So let me make sure I understand. This is not brine that's just going along the grain boundaries and the triple junctions. This is passing through channels which are bigger than the...
That's not completely understood in terms of what's the distribution of the fluid flow through the channels versus just all this. We have not looked at that. We don't understand. I wouldn't say we understand that.
It's specific to this columnar ice that's going to form.
The 5% is. I'll talk a little bit different kind of ice in a little bit.
I've not understood about the density. How can the seawater get on top of the ice?
Oh, because there's extra weight from the snow, on the snow. In other words, you're pushing the ice down so that it's a negative freeboard situation. This is very typical in the Antarctic. In other words, usually, like here's the...
Come out from top of the snow.
It floods the surface of the sea ice underneath the snow layer. So that bottom layer becomes all mushy, basically. Okay.
Doesn't come out on the surface.
Yeah, not on the surface of the snow. Right. That's right. That's right. Okay. So anyway, this is one of the dominant processes, particularly in the Antarctic. Also, salinity profiles change according to all the motion of fluid. Convection-enhanced thermal conductivity that I'll talk about in the second talk. And of course, the evolution of these melt ponds and sea ice albedo. All these important processes are essentially controlled by this on-off switch, basically. The algae that lives there, to see how dramatic this can be, biological activity turns on or off according to this rule of fives, and in particular the nutrient replenishment. This is a so-called convection-fueled algae bloom in the fall, and then essentially shut down. In other words, from that point on, that was the percolation threshold. There was an algae layer that was living here, critical isotherm, permeable, impermeable, come down, 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 down. And we calculated basically the day where it shut down, that was when the critical isotherm above which you're permeable, below which you're impermeable below, permeable below, and impermeable above. That was when that critical isotherm passed right through there, and they were stuck with the nutrients that they had. Okay, so why is this rule of fives true? It's a percolation threshold. Okay, so just a little about percolation theory. Oh, just also about timing. I guess I started at about, I think, 10.
How do you want to run it?
Yeah.
Yeah, you can go a few minutes over.
Okay, because I do have a little bit more here to go, but then it'll dovetail with the second half. Okay, so the basic percolation model, say a square two-dimensional lattice, a bond is open with probability P, closed with probability 1 minus P. The open bonds are black. This is an impermeable state. The electricity or fluid might try to get through here, but it gets stuck. Now this is P equal 2/3. This is a permeable state. And this is part of an infinite cluster of open bonds, and the minimal p, for which you have in the appearance of an infinite cluster and an infinite lattice, that's the threshold, which is 50% or 1/2 for the two-dimensional square lattice.
What's it for 3?
It depends on the model, but it's about like 31% or 35% depending on the site or the site of the bond. Okay, so but why is sea ice 5%? Why is molten rock 3%? What's going on? It's an excluded volume effect. The brine is not randomly distributed, which would be much closer to these lattice models, but there's an excluded volume effect, namely the grains of the ice. And the brine inclusions live on the boundaries of the grain of these individual grains. And so what I was able to do then, it turns out that this same kind of microstructure appears in what are called compressed powder microstructures that were used in the development of stealthy aircraft that they coat like the B-2 bomber with, or even the helicopters, the radar evading helicopters they used to go in bin Laden's compound to evade radar on the way in. And these are big polymer spheres and little metal or carbon black particles of given radii, and you squash them together and you can achieve percolation at very, very low volume fractions, much, much lower than the classical lattice models. And all I did was simply did a few measurements, right? Just did a few measurements, and then plugged it into their continuum percolation model. Out popped 5%, which explained all this data and all these things that we were finding. And in particular, because sea ice has this compressed powder structure of conducting inclusions surrounding insulating particles, big particles, sea ice is a radar-absorbing composite. That's why getting the thickness of the ice is such a hard thing. Using microwaves from satellites in space, it just gets absorbed. So you got to figure out all these other indirect and very clever methods for getting the thickness of sea ice. So just a word about order parameters in percolation theory. So this is the divergence of the correlation length, and this is a so-called universal critical exponent, nu, that measures the divergence of that correlation length as things become connected over larger and larger scales as you approach the threshold. But what's more important is the formula for the effective conductivity or the fluid permeability in this percolation model. And there's a so-called universal critical exponent T that I did a lot of work on earlier in my career. This was about for a slightly idealized model. I was able to prove an upper bound of 2 which was very significant in 3 dimensions, because the numerical estimates, there was a small industry in the physics literature, the numerical estimates went from 1.5 to 2.4, and then my estimate ruled out about 1/3 of those published numerical estimates. And then I was able to, there was about a 40-page paper in Communications and Mathematical Physics to actually prove all that. But in the continuum, you can have non-universal behavior where you do not have these universal critical exponents. And what I mean by universal is they do not depend on the details of the lattice, it only depends on the dimension. Okay, so then the next big step was to actually come up with theories, applied percolation theory, and these other Archie law types of things for the fluid permeability of the sea ice. And this is the cover of Geophysical Research Letters where we publish this. I like to view this as homogenization in action. How the microscale, that's about 1 centimeter across, this is our brine X-ray tomography, controls larger scale processes of interest in climate. We developed rigorous bounds that I showed you about, percolation theory, hierarchical models, network models, field data, but we also, just as importantly, most of what had been done before was slicing pieces of ice and taking photos. We developed an X-ray tomography method for the brine inclusions where we could really finely analyze the conductivity. This is some of our X-ray tomography. No pathways, one pathway, many pathways. And then eventually, so the science paper was 98. Finally, in 2009, X-ray tomography confirms that this rule of 5s really is true. We take 3D images of pores and throats, map it onto 3D graphs of nodes and edges, use finite size scaling techniques in physics to ultimately confirm this rule of 5s. This is the divergence here of the vertical correlation length, with diverging as you approach the 5% threshold. What's particularly interesting about this is the only real data that I know of for this. In other words, in a rock, at least in a sand, but maybe you guys have the technology actually. In a sandstone, like a regular sandstone that has pores in it, you can't just turn a knob and change the porosity of the rock with the air phase. But in sea ice, you can just slightly change the temperature and you can change, go through all these things. And so this is the only real data that I know of. There's, of course, hundreds of papers of numerical papers, but okay. Now, in the continuum, you can have non-universal behavior. In other words, the exponents are not their universal lattice values. And in particular, this Swiss cheese model, which kind of looks a little bit like some of the things that you guys are interested in, that's why I put it in here. The Swiss cheese model, you can have non-universal exponents, and it arises from these are like, you can map this onto a local conductance, and when you have singular distributions with a large enough exponent so that it diverges powerfully enough, you get non-universal behavior. However, in sea ice, this distribution more corresponds to the little areas of the brine inclusions is log normal, and then in that case, you actually, even though it's a continuum, you get the universal lattice value. And then there's another aspect. In other words, there's a scaling factor in front that comes in. Oops, right there. That scaling, the scaling factor for the permeability. This is not a fudge factor. We actually compute that from our X-ray tomography and a theory called critical path analysis that we kind of rediscovered, independently rediscovered some of this. It's a beautiful paper, AHL, coherent potential approximation, electronic hopping induction. And so we adapted all that, or actually used some of our ideas there to, it's like the bottlenecks control the flow, which I suspect is important in your guys' problem as well. And so then we were able to calculate from our X-ray tomography, a critical radius that is kind of the key bottleneck, and then that translates into a certain radius, and that gives us this factor in the front. There's the 5%. There's the universal lattice value. Okay, now sedimentary rocks like sandstones also live in what we would, as a statistical physicist, say, live in the same universality class with the same critical exponent. And then, of course, as I just mentioned, critical path analysis, originally developed in the context of hopping conduction and doped semiconductors, a nice example of cross-pollination, yields that scaling factor. And here you see we have excellent correspondence with, there's the theory, there's the statistical best fit of that data.
What is your dihedral angle?
I'm sorry?
What is the dihedral angle?
That I don't know. I don't know.
Between water and ice?
I don't know. I'm sorry.
15 degrees.
What?
15. Very low.
50.
15. Yeah. Okay, so let's see. So then we've also looked at these Archie law types of models. And so what we specifically looked at, this hierarchical structure that we have in sea ice, brine-coated spherical ice grains. So we basically get this with that same scaling, and so then we get this over a much larger range, because the percolation theory is only valid above the threshold. So we wanted to get a much broader range of applicability, and again, we get amazing correspondence between the data and the theory. We've also developed random pipe networks with these radii of the pipes chosen from these measured inclusion distributions, ultimately solved with fast multi-grid methods. We've done it for the electrical case as well as the fluid case. And then finally, I'm just about to quit. Just one little more wrinkle I wanted to tell you about. Might seem out of context, but it's not. So this is just a cartoon of the sea ice ecosystem with the killer whales trying to eat the penguins who live off the krill that live off of the algae living inside there. And this is an interesting biophysics issue in that these algae sort of coat themselves with this extracellular EPS, extracellular polymeric substance, like an algal mucus, because this is in a very extreme environment, that incredible variations in temperature and salinity, and this is how this helps them live. However, the presence of EPS changes the brine microstructure. And here you see all these fractally messed up inclusions due to the presence of this algal goop. And there's, and again, I know there's some really interesting mathematics as to how this is sort of the normal situation. It's basically how salt is flowing in and out of those dendritic structures, and the present how EPS kind of messes all that up. And anyway, but then from our point of view, in these terms of these network models, what happens is that's the log normal distribution of brine sizes that I told you about originally, the regular one, the normal one, without the algae. But now we've looked at new statistics of the sizes of the inclusions and you get this bimodal type of distribution. And so that's one result that we've come up with, and now now basically I have a PhD student who's working on a network model, our original network model, but how does the permeability structure change in the presence of EPS? And actually the last time I was in Antarctica, we tried to do experiments with that, but we just didn't have enough algae to do this. So that's one of the things I do have in mind. So I think that's it, right? And that's it for this part, and then if there's, I'll just pick up, when the coffee break is over, unless anybody has any more. Thanks.
Questions for Ken? Okay, so I've got one, although
Okay.
Which is this notion about getting the variational bounds
Yes.
for permeability, or not necessarily variational, but to get a priori bounds.
Yeah.
The thing that I've sort of always wondered about that is when you look at conductivity. Conductivity is intrinsic to the materials, in the sense that at the pore scale, each material has a conductivity.
Right.
The PDE that you'd write down at the pore scale has the same character as the PDE that you'd write down after homogenization.
Good point.
Whereas permeability, at the pore scale, permeability is not a well-defined concept. There is no permeability. You have the fluid and you have the pore network.
Right.
And so at the grain scale, you might write down the Stokes equations in the complex geometry.
Yes.
Which has no permeability, but then in the macro scale, you write down Darcy's law, which is, of course, a completely different character. And I'm just wondering, is that playing a role in the difficulty of getting these
That's a really good point. And that's certainly, from an intuitive standpoint, that's certainly part of the deal, part of the challenge, I think, Mathematically, I always point to that difference in the length scale issue, and I followed that up to trying to I have some other, approaches in mind that I'd like to, and you always run into that, that's the thing that causes the kind of the stumbling block as to where you want to go naturally, but it's like, oh, I've got this length scale in there, what am I going to do, So to me, that's always sort of the fundamental mathematical stumbling block. But what you're saying is absolutely true, and one of the fundamental challenges, at least, my intuition was built, unfortunately, my intuition was built up in the electricity magnetism world. And it took me a while, and I still don't have such a great intuition for the fluid permeability side, but anyway. And that's part of it.
Yeah, Stephen.
So all these results are specific to the concentration of salt it's in sea ice. So another parameter you could play with is you could change the concentration of your basic concentration of salt. And imagine an ocean with a smaller salinity, and presumably.
Okay. So first of all, the salinity of a hunk of sea ice. Take a hunk of sea ice, melt it down, and then a typical bulk salinity of that water is 5 parts per 1,006 up to 10, now down to 3 or something like that. Now, what determines that? The rate of growth. One of the main things is the rate of growth. That determines how much, I think is the answer to what you're asking, is how much salt is actually in there. Sorry?
From the top and growing this stuff downward into the sea at various rates.
Yes.
And that's going to exclude a certain amount of the salt.
Exactly. That's right.
And it's not easy to guess from thermodynamics alone.
I don't know myself, but there have to be at least empirical theory, empirical formulas and so on that will give it for a given rate of growth. How much salt can you expect?
The columnar structure is crucial to this.
Yes, and I will talk about a different structure which is more important in the Antarctic, the granular ice, but that'll be the second half.
So because Greenland has melt ponds and. It's not salty.
Oh, you mean up on the ice sheet? Absolutely. That's right.
Dirty, but it's not salty.
That's right. Oh, yeah, but the melt ponds on the surface, that's just basically melting snow. That's just melting snow.
And they drain through.
Yeah, it's very, and so many people have said, oh, Ken, you should work on ice sheets. There's so many of the same processes and structures and.
Pressure cracks and expansion cracks have a huge effect.
Absolutely, at least in these in the big glacial ice sheets. Yeah, sure.
I was thinking in the sea ice.
Oh well, there you get basically cracks, and this forms leads. The ice breaks apart. And now in terms of heat transfer from the ocean to the atmosphere in the wintertime, 90% of it comes up through the leads. So where these fracture patterns is really important for understanding thermodynamics.
That's on a huge scale.
That's on a much, exactly.
Small scale.
That's right, yeah.
Maybe one more question. Sash, did you have a?
Well, I was just wondering, and you're probably going to talk about it later on. You were talking about the melt pond evolution.
Yes.
So are you going to touch that?
Oh, absolutely. The last part of the talk is about melt. It's not a heavy-duty version of my melt pond stuff, but I'll touch on the main issues. And by the way, I view melt ponds as big brine inclusions. I know they're not salty, but it's like the whole thing's in equilibrium. You know, in other words, it's like an equilibrium.
What sort of length scales are these?
Yielding many orders of magnitude, from just little ponds like this to kilometer scale types of structures, and that will be part of the issue. Yeah. So, okay, well.
Okay, so let's break for coffee.
Great.